In our last video, we have seen an example of learning of a multi-layered perceptron for some problem, and we have also seen that how the synaptic weights between various layers actually changes during this learning process. And we have also observed that this learning process, if you want to implement these learning steps, these are nothing but some series of matrix computation. And finally, after some set of iterations, we can get a a learned correct model that can clearly distinguish between two or three set of classes, depends on the data set. So now today we will enter in a very vital part of during this learning that we have not yet discussed. That is what we call regularization. Now, before we understand what exactly regularization is, let's try to realize it from an example. You see, just watch the leftmost picture. We have some set of points, some number of matches on versus age of some particular sportsman, or so of many sportsmen actually. And suppose the data set, according to the data, the points are something like that we can see over here. Now, so the points is something like this. Now, if I tell you that you draw a straight line that can actually touch most of the points, so maybe your straight line will be something like this. Best straight line will be something like this, where the equation of the straight line can be something like theta 0 plus theta 1 into h. So this is nothing but a simple equation, something like y equal to mx plus c, where this is the c and this is your m, and we can easily understand that these theta 1 and theta 0 are the free parameters that we can tune through this learning process, and finally I can get the straight line like this. But problem is that this straight line doesn't enough reflect the exact curve that touch all the points, because the points given in this set is little bit nonlinear. That's why it's better to, if we use more variable, more free parameters, then it can be something like this also. So we can have an equation something like this that is given over here, and due to some value of theta 0, theta 1, theta 2 and theta 3 and theta 4, ultimately assume that you have found a curve something like this. Now, from this diagram you can say that, okay, yes, this curve actually easily connect each and every points of the set. So that was actually our goal, to to minimize the error between the actual point value and output, that is the output from the model. So according to the model output, the curve is something like this. That's why you can see the error will become 0. But you know, this particular curve may fit very well for the training data set, but if you consider there is a point somewhere over here, then according to the curve, it will be not good to estimate the corresponding probable age if the match on is something like this point. So in case of test result, I mean train result, the model will give outstanding performance. But in case of test dataset, the model will not give a very good performance. The two cases that we have seen, two are actually extreme cases. In one cases, it has not even touched all the points, and in second case, it has touched all the points. But problem is that in both cases, the result is not going to good for test dataset. And these two extreme cases are considered as underfit and overfit. The concept of overfitting we have already seen in our previous lecture. So if you have a very, I mean, it's not clear in your mind what does overfitting mean, maybe you can go back to my previous lecture and you can check it. Now, in any model, this overfitting and underfitting both are not expected. Both actually tell you, both actually show that the model has learned well, but it doesn't really learn well for the test dataset. So model will fail for predicting some unknown data. That's why we need something like a trade-off between this underfitting and overfitting, and that is what we call actually balanced fit. That is written in the right balanced, sorry, in the right side, balanced fit. In case of balanced fit, you see, before you can see that the curve is something like this, which has not yet touched all the points, but still I can say it's balanced fit because this curve can capture the non-linearity between the points in the whole feature space. That's why this curve can show a general behavior of the training dataset. Now, if this general nonlinear behavior is almost same in case of test dataset, then I can say that in case of test dataset, the result will be also correct, most as much as correct as possible. And you see, just try to relate these two. We can see that yes, theta 0, theta 1 is not sufficient. These two are not sufficient to represent a curve something like this. Even these 5 are not required to represent a curve like this. These are too much. And if you see, if you somehow keep this theta 3 and theta 4 as 0, I will get the similar equation which is representing a balanced fit curve something like this. That means somehow during learning it is not necessarily true that all the synaptic weights will have some value. In some cases, you may need to, it may happen that due to get this balanced fit, we need to keep some synaptic weights as 0. For example, in this case, just if you put 0 in theta 3 and 0 in theta 4, you will get this equation. Now question is that who will give this 0? Should I give? I cannot give it as a programmer, because when I am writing a MLP program, I mean executing that, the weight changes is not happening according to my wish. It is happening mathematically. So whether a synaptic weight becomes 0 or whether a synaptic weight becomes very large, that totally depends upon the situation. So that means somehow we have to restrict stopping the learning process until we get something. If we have some value in theta 3 and theta 4, we cannot stop our learning, because if we consider the current value of theta 0 to theta 4 in this equation, and if I get this curve, so strategically you will see that there is no error between the desired output and the actual output from the model, which is 0. So if your error is 0, naturally you can stop, because if your error is 0, that model is identifying correctly everything. But it is not true for all the cases that we have seen. That means somehow I have to restrict stopping. That means if we find this situation, I have to add some extra penalty with the error measure so that the learning process doesn't converge. First point. So that means what we can do. This is just what we have discussed over here, that if we make this 2 as 0, then I will get a curve something like this. So how we can do this? Here the regularization formulation comes. So we have to add some extra penalty in the error function, and that will basically help you to alter some specific weight update equations during this learning process. The first point is that initially the MSE was something like this that we have seen. Actually, yes, MSE, I mean some square error and their average. And there are two different type of regularization. Especially we have one we call L2 regularization and another is called L1 regularization. In case of L2 regularization, what we do, we add this an extra penalty in the error function, where this lambda is basically you can say a regulator. You can assume in this way a regulator. The purpose of the regulator is to increase or decrease the influence of something. So how much weight increment will influence the MAC, that depends upon this lambda value. So this lambda value always I mean lie between 0 and 1. If it is 0, that means if it is 0, that means there is no influence of this regularization parameter in this learning process, and if it is 1, that means it has a strong influence. So although this di minus yi will show no error in that situation, like in this situation, but due to the w's, some high value of theta 3 and theta 4, this will not become 0. That means in that case the error will not become zero and you can continue the learning. The question is that how it will affect the weight updation rule. Actually, you see, the weight updation rule actually started from this equation. If you go back to my previous video of the derivation of the backpropagation uh, technique, you will see that the calculation of the weight updation rules were started from derivation of this error. So if we add something more with this error function, that will alter some of the equations in the derivation, weight updation rules. Now I have not written what will be the exact reflection on the weight updation rule. If you have a clear idea about the derivation, you can easily calculate it by your copy, in your copy, that where this will reflect. So it is my suggestion that just take a copy. After this class, take a copy. First you derive normally what we have done in backpropagation derivation, and then you add this one, and accordingly you update those those equations where some part of this one will get reflected. And second one is that L1 regularization, and you see that L1 regularization is basically almost same as L2, just only difference is that L1 take only absolute value of the W. So actually why this L1 is given, because is that sometimes we can see that L2 regularization actually in some cases actually puts zero, almost zero forcefully in some ways. But in case of feature selection, you know, putting considering exact zero in some feature value may affect the property of the object. About property of the pattern. That's why what we do, sometimes we try to keep the minimum value of some of those features as much as possible, but not zero. So in that case, this L1 regularization plays a beautiful role, and that's why we use this one. And according to this equation, obviously, for L1 regularization, in some part of the backpropagation derivation, in the weight updation rule, there will be a small effects, and you can easily identify that if you derive it in your copy. So now we will start one more very important part of this learning process, that is what we call normalization. What is normalization? Let's see. Normalization is a technique often applied as a part of data preparation for machine learning. You see, it's part of data preparation. Before you start your implementation, before you start your execution, you have to do it on your data set. And what is written? The goal of the normalization is to change the values of numeric columns in the dataset to a common scale without distorting differences in the range of values. So we are actually trying to, keep them in a particular scale so that they have the same effect on the model. Now, why I am trying to say this? Why I'm trying to do this? Let's try to realize from a example, a very simple example. Let's take a situation something like this. So just assume that we have a neural network over here, okay, and maybe just there is two outputs, just a SLP. I'm considering a single layer perceptron. It's not important to do. I mean, normalization is not something associated with MLP only. It's actually associated with any machine learning model. So just we can try to understand this one from example of SLP also. So suppose we have these connections, right? Like this, and here we have the inputs, and from here we have the output. So suppose x1, x2, xn, and it is y1 and y2. Now suppose this x, these are actually, this is a feature, right? So this is feature 1, this is feature 2, this is feature n. Now suppose that means a particular pattern p1 is represented by n features, right? So among these n features, suppose this x1 feature value lie between say 100 to 200, x2 feature lie between 0 to 5, and x3 feature, sorry, xn feature in this way say lie between say 0 to 0.5, 0.5. Now you see, just take an example of this, some values in between this range of some pattern. Suppose here the input is say 150, and here the input is 2, and here the input is 0.05, suppose. Okay, it can be. Now see, whatever the weight, it doesn't matter over here, some weight is present. If I still assume this weight present between in this particular part is very small, then also due to this very large value of this feature, what will happen? In this particular node, this node is actually taking input from all these input neurons, right? And in this input neuron, since this feature value is very large than other feature value, what will happen? Always this particular input will try to dominate the this particular output y1, which should not be a a good situation at the time of learning, because a pattern, in a particular pattern, you cannot uh, you cannot give an importance to a particular feature, because a particular feature doesn't have any existence without the pattern. A pattern represented by all the features, and in fact each and every feature should have the same importance. And we can see that this similar importance is not possible to find out, is not possible to represent if we have a very large value in a particular feature and a very small value in another feature. So according to this situation, I can easily say that x1 will always dominate xn, because only because of this range. And that's why there will be always you know uh, chance to get a biased learning due to the feature values of x1, which is not true, which should not be true. That's why what we do, we try to keep them in a particular scale for all the features so that no feature can dominate other feature. And that's why that is the purpose of this normalization technique. And that's why actually we try to change the values of numeric columns is represented in the data set in a common scale. You see, that common scale can be 0 to 1, can be minus 1 to plus 1, can be 0 to 5, but something common. And this is should be done before you start the execution. So you will have an entire data set, you have a data set, something like this. Suppose there is some columns that has to be normalized first, then this particular one should be used for MLP learning. Now, how we can do this normalization? There are various techniques actually. You see, take an example, something like this. I mean, just what actually I was discussing. So you have data set of some person whose gender is, I mean, male and female with various heights, weights, and ages. And you see, the height actually can dominate this weight and age because height range, you see, it's a very high range than the weight and age. So it may become a problem. So somehow we have to keep these columns in a common scale, all these columns, this column, this column, this column, all. And that's why we can use one of these normalization formulas. This normalization formulation you can find out in internet easily. In generally, I can say that we use a normalization either this particular one or this one. This particular normalization is highly used in most of the learning process, and also this one is used. Even, I'm not saying that these other options are not correct. I'm saying that in most of the cases, either this one or this one is used, and in some cases, I mean, there is a possibility to use one of this approach also. And what is this? Now what is this? This is, I hope you can see statistically, it is a standard deviation, it is a mean. So this x is what? X is the actual value of the particular feature of a particular pattern, and mean is that mean of the whole, you know, range, I mean, in the set, in that particular column. So mean is the mean of all the feature values of that particular feature. And standard deviation is also, you can easily find that. Now, and in this case, in min-max feature scaling, this x is representing the actual value and x mean is the minimum value that is representing represented in the data set. Similarly, x max represent the maximum value. So if we just consider considering this one, say this particular one, I want to scale it in between 0 to 1. You see, always remember one thing, this particular technique actually scales everything in 0 to 1. You see, it's written. Okay, it's written. So, and if you want to, put them in a particular arbitrary order A and B, then you have to use this formula. Okay. And if you want to keep them only in between 0 and 1, this will. That means the minimum one will be represented by 0, maximum one in the set will be represented by 1, and other value will be actually in between some value 0 and 1. So I can easily say that here this one, this 165 is going to be 0, because it's very easy to realize. Let's just that is x dash was x minus x min by x max x min. So here x min is 165 because this is the minimum one, and I'm trying to scale this one, right? So x itself x min, that means x min minus x min will become 0. See, if the upper part is 0, obviously this part will become 0. So that's why this is 1. And if I consider this 170, this is the highest value in the whole set, right? In the whole column. So I can say this is basically the maximum value. That means x max is 170, right? So if you want to scale this 170, this x, then in that case representing x max. So that means x max minus x min. And in the denominator we have x max minus x min. So if you divide it equal to 1. So you can easily say that this will basically scale in between 0 to 1. And other values, for example 164 will be some value, because it will become 164. Oh, I'm sorry, 164 is lesser than 165. So this will become 0. Actually, this is the minimum one. So if you considering 165 as an input, so that means in that case it will be 165 minus 164 by 170 minus 164 equal to this is 1 and this is 6, right? 6. So that means 0.33, something like this, right? Am I correct? No, I think. No, it's 1 by 6 equal to 0.33 or not. Let's see. 0.17 actually. 0.32 will be its 1 by 3. Sorry, 0.17. 1666, so 17. So that means this will become represented by 0.17 like this. Now this is not only for this column. The same thing will have to be for this part also. Will be this part also, but separately. Don't mix up two columns. You cannot compute 170 value with respect to this row. You cannot do that. You have to do for a particular feature, for a particular column. Now, to do this, what will happen? Obviously, we will see that this particular feature value, we can easily say this particular x1 will be represented some value, I say 0.62. This x will be represented by 0.24. This will be represented by 0.1. Now you see 0.64 and 0.1 doesn't have, 0.64 have not a doesn't have a way, way to influence much more than this one. They are almost in the same scale. That's why automatically your, you know, the way when uh, you will train a MLP, your learning will be fine, and that is the purpose of regularization. So these are the two things that you have to keep important in your when you will train a MLP. And one more thing is there that I forgot to write over here. I mean, let's do one thing. Let's write here. I mean, that is important. So what we have seen that basically we can assume the MLP as a process of learning I mean, just as a process of a for loop. If you want to implement this, it is nothing but a a while loop. While say uh, error is greater than threshold, here it is apply backpropagation, right? That's all. So it's a while loop, simple loop, not while, maybe for, doesn't matter, but some a loop. This is the learning process. Now one more thing is there, that is, you see, try to realize it from your own situation. That is, when you read a particular book, you learn some couple of chapters, and if I ask you something, maybe you will able to answer some of the questions from those chapter, and you may not be able to answer some other questions, and you can make your performance better in most of the cases if you reread those set of chapters once more, and that you do frequently, right? You start from chapter 1 to 5 and you again read chapter 1 to 5 after some couple of time. So that means, and what this while loop is doing, this while loop is actually taking this pattern one by one. So if we have a data set having say 1,000 patterns in a training data set, we have 1,000 patterns. So what we are doing in this loop, we are feeding these patterns one by one. That means I can say that this pattern should run 100,000 times, because after 1,001 pattern is not present. So after 1,000 times the loop will run. Then what to do? We should feed the first pattern again. That means you can assume in this way, like let's rewrite the part of the loop again here. Uh, just try to realize it, that suppose I'm just writing that while pattern number, just I'm writing in an abstract way, okay, the pattern number is less than 1,000, equal to 1,000. This pattern number started from 1, okay, that apply backpropagation. Okay, but as soon as this pattern number 1,000 will get completed, what to do? We have to restart again. Just like you have completed chapter 1 to 5 and again you are reading from 1 to 5. So beyond this loop, we must have one more loop, which will think about some set of times. Now, how many times you can do that? You have to repeat that. If you ask me, Then how many times you will reread this chapter 1 to 5? I will tell you that till you will not able to answer everything. Like you have read 1 to 5, I asked you some question. You have some performance say 0.7. According to my questions, then your answer. You have read it this chapter 1 to 5 again. Your performance increased from 0.7 to 0.85. I will tell you read it again. Again you will do that. Your performance increased from 0.85 to 0.95. Again I will tell you like this. And when I will see that maybe your performance is 0.99, I mean 99% question you have successfully answered, I will say okay, you have correctly learned, you don't need to read it. That means here this error I can put that here, that means while the error greater than the threshold till you go on these 1000 patterns. So this loop, this is what actually we called epoch. Technically, in case of learning of an MLP, we say it as an epoch. Epoch is means a chapter. A chapter in the sense you are learning chapter 1 to 5, it's an episode. It's a one epoch. Again you are rereading chapter 1 to 5, epoch number 2. Again you are reading 1 to 5, epoch number 3. In this way, in some cases, you need a large number of epoch to train a MLP if that pattern is very complex. So when you will design an MLP, you will write those set of matrix computations easily that we have seen in my previous video. Not only writing those instructions is important, you must remember this structure at the time of executing your MLP. I mean at the time of executing uh, your model for learning. And when this error threshold will come beyond this threshold, so automatically your model will converge. That means your model has learned well, so your model will stop, and then you can start your testing. You can start your testing to see that whether how much actually your model has learned well. Okay, so in this way actually you can write your program. So we can stop our class over here regarding, over after this two, and we will see what to do in the next class. Thank you.